page 234, section 4.2, we're talking about the mean value theorem. It says we're going to see that many of the results of this chapter depend on one central fact, the mean value theorem. But to arrive at the mean value theorem, we're first going to need to know Rolle's theorem, okay? Now, this is comical to me. If you'll notice out there in the margin of your book, you know how they always give you the little history lessons about the mathematicians. So out there it says Rolle's theorem was first published in 1691 by the French mathematician Michael Rolle. Skip down. Later, however, he became a vocal critic of the methods of his day and attacked calculus as being a collection of ingenious fallacies. So, it's comical to me that, you know, we have this theorem that is pivotal for the mean value theorem, that is pivotal for all kinds of things we do in calculus, and yet the guy who came up with this finally decided that, you know, calculus was just a bunch of fallacies. So. Any case, all right, so here's what Rolle's theorem says. If you have a function that satisfies three hypotheses, then there will be a number c in your open interval AB where the derivative is equal to 0. If you have a function within an interval that meets these three hypotheses, then there will be a number in that interval where the derivative equals 0 at that number. Okay, what are the three hypotheses? Well, the first one is that the function is continuous on the closed interval. The second one is that the function is differentiable on the open interval. And the third is that f of a has to equal f of b. So we're going on the interval from a to b. F of a has got to equal f of b. Now, let's think about all of the different ways that we could draw that out, okay? If f of a has to equal f of b, the y values have to be the same. So basically, I'm starting and stopping at the same height. The only way that I could connect those with a smooth, continuous, differentiable curve is if I drew a straight line, or maybe I had something that had a relative maximum or something that had a relative minimum, or maybe it had multiple maximums and minimums. But that's really all of the scenarios that I could have, right? In every single one of those scenarios, you'll notice that I would be able to draw a horizontal tangent line where the derivative would be equal to 0. So we can see why Rolle's theorem makes sense, that there would have to be at least one number in that interval where the derivative equals 0. The reason that these hypotheses are so important is, first off, if the function weren't continuous, maybe right here at this one point where I'm going to have my derivative equal 0, maybe there's a hole in the function right there because it's discontinuous there. That would be a problem for Rolle's theorem. Same thing with differentiability. If I came and I had a vertical tangent at the one point where I'm going to have a horizontal tangent line, that would cause a problem for Rolle's theorem. So, you know, you can see here why those hypotheses are significant. So, when it comes to your test, this is what it's going to look like. You're going to have two columns. The first column, you're going to go through and you're going to list what the three hypotheses are. So literally you would go through and say the function has to be continuous on the closed interval 1 to 4, whatever yours might be. It has to be differentiable on the open interval 1 to 4, and f of 1 has to equal f of 4. That's what you're going to put in the first column. Then in the second column, you're going to have to justify that, because I can't use Rolle's theorem unless I can prove that it's true, that I can justify that those hypotheses are valid. So I'm going to need to go back perhaps and look back over my rules for continuity and differentiability. Like if the function that they give me is a rational function, where are rational functions continuous and differentiable? That's something we've already studied that we should know. Where are trig functions continuous and differentiable? Okay, what are the rules for differentiability and continuity as it applies to those different types of functions? Right? So in our case, the function that they gave me here was a polynomial. So if we go through to verify or justify that first hypothesis, we could just say all polynomials are continuous everywhere. The same thing is true for the second hypothesis, where they say it has to be differentiable. I could say this is a polynomial and it's differentiable everywhere. Unfortunately, both of the examples that they gave us in the text were polynomials. And that's not really going to help me. So let's rabbit trail for just a second and let's look at, what if my function wasn't a polynomial? What kind of things am I supposed to be writing for these justifications so I make sure I'm doing what I'm supposed to do? Okay? So again, numbers 1, 2, and 3, the hypotheses are not going to change. I'm just going to list those hypotheses. That's just my memory check to make sure that you have memorized, that you know what those 3 hypotheses are. But for your justification, let's say that your original function had been a rational function, 1 over x minus 3 instead, okay? So then for number 1, when you're trying to justify that the function is continuous, you have to know the rule for continuity about rational functions. The rule that we learned was that rational functions are continuous within their domain. So I'm going to state that as my justification. Rational functions are continuous in their domain. But I'm not done. You got to tell what the domain is then. Don't leave me hanging. If you're saying it's continuous in its domain, great. What's its domain? So I can look at this and say, okay, just like anything else, it's going to be, the domain's going to be it's going to be all real numbers except for where I have 0 in the denominator or negative under a square root, right? So I'm going to, or a fourth root. I'm going to have to get rid of the 0 in the denominator then. So my domain is going to be all real numbers except for 3. So if 3 is in my interval, I'm toast. If 3 is not in my interval, I'm okay. So I got to write something about that too, where I could say, okay, my interval just went from 0 to 2. So even though it's not continuous at 3, that's okay because it's not in my interval. That is what I would have to write for my justification on the test. So yeah, in the example that they give us, it's a polynomial. I don't have any problems. I can just say, oh, polynomials are continuous everywhere. But what if it's not? What if they give me a root function or a rational function or something else that's not continuous everywhere? Then here's what I need to write. I need to write the rule about continuity for that function. In this case, rational functions are continuous in their domain. And then you're going to need to state the domain of your function if it's limited to only being continuous in its domain, like root functions and that type of thing are. So I would need to state the domain, and then I need to check and see if there are any exclusions. Make sure those exclusions are not in your interval. Because if you cannot verify the hypothesis, if all 3 of these hypotheses can't be verified, then Rolle's theorem fails. I can't use it. All right, so then the second thing is the function differentiable on the open interval. Of course, we had a polynomial that was differentiable everywhere, but let's go back to what if I had a rational function. The easiest way to prove differentiability is to just take the derivative. So if I took the derivative of this function, its derivative is negative 1 over x minus 3 squared. So then it's not differentiable anywhere you get 0 in the denominator or negative under a square root or fourth root, even indexed radical, right? Or if it's a piecewise defined, always have to check where the pieces come together. So in this case, I could go through then and say, okay, since this is my derivative, I don't have to state a rule about differentiability or anything like that. I can just say this is my derivative, and you can see that derivative is going to exist everywhere except for at 3, so it's not differentiable at 3. But again, that wasn't in my interval, so I'm okay. That's what I'll be looking for on your test. So I wanted to make it really clear for you as you're practicing the homework tonight what to write so that you know what you need to do for your test as well. Okay, so let's go back to the problem that we actually were given now that we've kind of gone off and discussed this. The third thing that we need to prove is that f of a is equal to f of b. So a was 0, b was 2. So let's plug 0 into the function. So that would give me 0 minus 0 plus 2 plus 5, or sorry, plus 0 plus 5. So f of 0 is 5. And then we could go back and plug 2 into the function, and we'll also get 5. So I've been able to verify that all 3 hypotheses are true. Since they are, then I can use Rolle's theorem. And Rolle's theorem just says that somewhere in that interval, your derivative at a point will equal 0. Find that point. Okay? So let's take the derivative. So derivative of x cubed is 3x squared. Derivative of negative of 3x squared is negative 6x, and derivative of 2x is 2, derivative of 5 is 0. Set that equal to 0 and solve. And if I had my calculator, I could use the quadratic formula. If not, I could do quadratic by hand. No worries. And so I'm going to get these two solutions. And sure enough, if I graph that cubic equation, it has a maximum and a minimum. And that means that I would have horizontal tangent lines at those places, and they just so happen to be at these two x values. So I could check that by throwing this into my calculator and maybe using my max and min buttons. But this gives me a way to find those values without having to do it on my calculator. All right, example 2 is the converse of Rolle's theorem. Example 2 says, prove that the equation x cubed plus x minus 1 equals 0 has exactly one real root. Okay, now we're going to need to back up to the intermediate value theorem. We've used the intermediate value theorem before to prove that something has a root, but we couldn't prove that it had only one root. Okay? So let's start with what we already know how to do. Let's start with using the intermediate value theorem to figure out whether there's even a root for this thing or not. When we did intermediate value theorem, we said it had to be a continuous function and there had to be a sign change. That's what we were looking for. Those were the two keys. So I've got a polynomial that's obviously continuous everywhere. And I just started by plugging in values. So when I plugged in 0 and I plugged in 1, I got a sign change. I got lucky. They're not going to give me something random like a sign change between 26 and 27. So it should, somewhere between -3 and +3 most likely. If I, just plug in a few values, I'll find my sign change. So here's what the intermediate value theorem had said. If you have a continuous function, if there is a y value between these two y values, then there's going to have to be an x value that goes along with it between these two x values. And the way that we applied that to this scenario was we said, okay, if we change from negative to positive or from positive to negative, the only way you can do that is with going through 0. So I know that I have to have a y value of 0 in between these two y values, and according to the intermediate value theorem, then there would have to be an x value in between 0 and 1, where f of a is equal to 0. That's a root. So we've shown that there's a root between 0 and 1. We had done that before. What this is asking me to do is to show that there is exactly one root, because with the intermediate value theorem, there could be more than one. We want to show there's exactly one. And so here's what we can do. We can go through, and according to Rolle's theorem, there should be at least one number in the interval where the derivative equals 0. Okay, so let's take our derivative and set it equal to 0. So derivative of x cubed, derivative of x, derivative of -1. Set that equal to 0. How am I going to solve that? Subtract 1 and divide by 3. Good. All right, then what? Take the square root and be sure you put in plus or minus. All right, so I'm going to get plus or minus the square root of -1/3. What kind of answers did I just get? Imaginary. I didn't get any real solutions. Hang on. There is at least one number in that interval where the derivative equals 0. I didn't get a real number in that interval. That means the Rolle's theorem just failed. And the only way that Rolle's theorem can fail is if one of these three hypotheses is not true. So I just proved, again, we're going about this kind of backwards. We're kind of using the converse idea here, where we're saying, okay, I just found out that there is not a number c in the interval where the derivative equals 0. That means Rolle's theorem fails. That means one of these three hypotheses cannot be true. All right? Since this is a polynomial, I know that it has to be continuous, because all polynomials are continuous everywhere. And I know it has to be differentiable, because all polynomials are differentiable everywhere. So the only thing that leaves is that f of a can't be equal to f of b. So there are not two zeros. There's only one. Okay? All right. let's look at the mean value theorem. Mean value theorem is over on page 235, and it starts the same way. The first two hypotheses are the same. So I need to show the functions continuous on the closed interval and differentiable on the open interval. So again, on your test, same scenario. You would list those two hypotheses for me as numbers 1 and 2, and then right beside it, you would list the justifications for those. And you would be doing that same thing we did with the polynomials or that we did with the rational function, exact same thing. So again, they gave us a polynomial here, so it was easy for us to say all polynomials are continuous everywhere, and all polynomials are differentiable everywhere. Rather than saying all polynomials are differentiable everywhere, just as a reminder, I went ahead and took the derivative here because the easiest way to see differentiability is just to look at your derivative. The only place it's not differentiable is 0 in the denominator, negative under an even indexed radical, or where two pieces of a piecewise defined don't meet when they come together. So easiest way to find differentiability is to take that derivative. Okay, so we verified the two hypotheses. So now I know that the mean value theorem will be true. Great, what is the mean value theorem? It says if those things are true, and they are, then there is at least one number c in your interval where the derivative at c will be equal to f of b minus f of a over b minus a. What's this right here? What's that the formula for? Slope, yeah. So basically what they're saying is there's going to be some point where the slope of your tangent line derivative, right, is equal to the slope of the line that connects your 2 points. I mean, look at it. If this is a f of a and this is b f of b, and I connect those with a straight line, somewhere on that curve there's going to be a point where if I drew a tangent line at that point, it would be parallel to that line. They would have the same slope. That's what the mean value theorem is helping me find. Okay? So we can go through then, and if you're not a fraction fan, you could multiply both sides of this by b minus a and write it in this form. So you'll see the mean value theorem written both of these ways. So the one that they're using in the textbook is the second version here, so we'll go with that. So we could go through then and we could say, okay, a was 0 and b was 2. So let's put those in. 2 for b, 0 for a, 2 for b, 0 for a. So what do I get when I plug 2 in for x? 6, 2 cubed minus 2. So I'm going to get 8 minus 2, or 6. And then when I plug 0 in, of course, I just get 0. So I'm going to have 6 is equal to the derivative times 2. Let's divide both sides of that by 2, and I'll get the derivative is equal to 3. Now, if you had gone through and you had done y2 minus y1 over x2 minus x1, I mean, again, our points are 0, 0, and 2, 6. So if you had done y2 minus y1 over x2 minus x1, you would have gotten 6 over 2, you would have gotten 3, right? So that's that other formula, the derivative is equal to the slope. So we have the derivative is equal to 3. Okay. So now I want to figure out where that is. Where is the derivative equal to 3? We've already taken our derivative up here. It's 3x squared minus 1. So we want to figure out where that derivative is equal to 3. So how do you want to solve? Which one do first? All right, let's add 1, divide by 3, and take the square root. Perfect. So we'll add 1 to get 4, divide by 3, take the square root, don't forget your plus or minus. And we could simplify that numerator, but that's going to leave us a radical in the denominator. So we could rationalize that and say the square root of 4 is 2 over the square root of 3. And so rationalize that to be 2 square roots of 3 over 3. And I need to find a decimal for that to see if it's in my interval or not. So the decimal would be 1.15. So are both of those in my interval from 0 to 2? I have 1.15 and negative 1.15. Are they both in my interval? No. So what will happen is you'll work this out and you'll get 2 answers, and you'll look in the back of the book and they'll only have 1 answer, and you'll think, what did I do wrong? You didn't do anything wrong. Just check to see if maybe the other answer you got is not in your interval. Okay. All right. So what the mean value theorem is telling me is that at the point x is equal to 1.15, if we gave a decimal approximation for this, at that point, the slope of the line connecting my starting point and stopping point is the same as the slope of the tangent line, the derivative. And so if I actually throw this into my calculator, here's the graph of that original function. And we were going from 0, 0 to 2, 6. So if I connect that, there's that line that had a slope of 3. And sure enough, at the point 1.15, I could draw a tangent line that is parallel to that line. That's what the theorem helped me find. Now, I know right now, it's kind of like, okay, so what? Why do I need to know that? Well, we're going to have lots of applications of that theorem. So we just want to make sure we understand the theorem right now. Okay, then a couple of other things that they tell us on the bottom of page 237, theorem number 5 says, if your derivative equals 0 for all x values in an interval, then your function must be constant on that interval. If every derivative is 0, the derivative of a constant is 0, right? So if every derivative in your interval is 0, then every value in your interval must be a constant. And so that's all they're saying. And then over on 238, it says, if the derivative of f of x is equal to the derivative of g of x for all x in an interval, then f minus g is constant on that interval. That is, f of x is equal to g of x plus c, where c is a constant. All right, let's throw some equations into that, and it'll make a lot more sense. Let's say that f of x is x squared plus 2, and g of x is x squared. The derivative of f of x, we would say the derivative of x squared is 2x, and the derivative of 2 is 0. The derivative of x squared is 2x. So yeah, those two derivatives are equal to each other. So if the derivative of f of x equals the derivative of g of x for all x values in a particular interval, then if you took one function and subtracted the other, the only difference between them could be a constant. And sure enough, if I take f of x and I subtract g of x, x squared plus 2 minus x squared just leaves me 2, a constant. Because the idea is if their derivatives are the same but the original functions aren't the same, the only difference between them could have been a constant value, because when you take the derivative of a constant, you get 0. And so it would become a moot point. It would drop out of the scenario. The other way that they've stated that is that f of x is equal to g of x plus c. So sure enough, if I take g of x and I add a constant c to it, I do get f of x. So again, it makes more sense when we actually see some values plugged into it. All right, so here is our homework for tonight on pages 238 to 239.